everybody. We are going to work through how to do these last two pre-lab questions for your pre-lab about springs and work. So let me share the screen with you so I can show you what I'm talking about. All right, so questions 3 and 4 for this pre-lab. We're going to talk about work, which you haven't really encountered, might not have encountered by now, depending on when you have this lab. Work is the application of a force over a distance. If you have a constant force, then the work is just going to be the force times the distance over which you've applied that force. You apply a force over some distance, the force times the distance gives you the work. Okay, so D is the distance over which our constant force is applied. F is our force, and the unit for work is a unit of joules. So we need our force in newtons, we need our distance in meters in order so that when they multiply each other by each other, we get our work in joules. It's spelled J-O-U-L-E. Okay, so that's if you have a constant force, but most forces in nature are not constant. Consider a situation in which our force is not constant and you must do the work in small increments. So the total work that you do is going to be equal to the force that you apply over a tiny distance, plus the force that you apply whenever you apply a different amount of force times that tiny distance over which you've applied that force, and so on, all the way out to however many times you change that force, the distance over which that force was applied. So we can generalize this to say that work is equal to the sum of all of our little increments of force times distance. Okay, and I will show you that this is sometimes what we refer to as a Riemann sum for any of you who have had calculus. Okay, we often will do this with data. We're essentially here in this, what I'm going to show you, is taking an integral, an area underneath a curve by hand. Imagine that we have a spring and we stretch it over increments of distance. This is what we're going to do in the lab this week. The data might look like this table below. Okay, and here what I'm classifying as x sub I is the total distance you have stretched the spring from equilibrium at each step I. So we're going to do many different steps. Fi is the reading of your force gauge pulling the spring at that instant. So the force gauge are those little green things that have the spring inside, and when you pull on them, they measure a force, and that you have in your lab kits. And Di is the amount by which the spring has been stretched from our previous measurement. So then the work we can calculate for each step, and that work is going to be, for each step is the force that's been applied at each step times the distance over which the incremental distance over which that force was applied. Okay, so you might be supplied with a set of data like this. I represents our step or the part of our experiment. So we're taking measurements at a point 1, 2, 3, and 4. So we're taking 3 different measurements. That's what that little I here means. Okay, we're taking a measurement at 1, 2, 3, and 4. We're calling measurements 1, 2, 3, and 4. Okay, so for our first measurement, the distance that we stretch our spring in total, the total distance that we stretch our spring from 0 centimeters is 1.1 centimeters. The total force we have to apply to stretch that spring by 1.1 centimeters is 227 newtons. Okay, and then for the next step, we're going to stretch our spring again and take a second measurement. The next time, we're going to stretch our spring 2.2 centimeters from the 0 mark. Okay, and it takes us 440 newtons of force to move the spring 2.2 centimeters from where I say x is equal to 0. Then now we have to calculate the work done at each step. Remember, the work is the force at that step times the incremental distance over which that force was applied. So we have just this total distance we stretch from equilibrium. not the incremental distance between consecutive measurements. That is what we want for DI here. So for DI, we have to calculate the distance over which we have stretched the spring from the previous instant, okay? The amount by which the spring was stretched from the previous measurement. So if we're starting at equilibrium, the first one is easy. If we're starting at equilibrium for our first measurement, we had to stretch the spring 1.1 centimeters. Then for the second measurement, the incremental distance you stretched the spring from the previous step. To find that, you go over here and you subtract our 2.2 centimeters from 1.1 centimeters to give us this, okay? That's the amount by which the spring has been stretched from the previous measurement. And then for our third measurement to get DI, we have to come over here and we take, we had to stretch our spring for the third measurement, 3.4 centimeters. We subtract that from the previous measurement, which was taken at 2.2 centimeters. The difference between those is 1.2 centimeters. That's what we use here for DI, okay? And then you do a similar thing for 4, okay? And so then the work done in that step is going to be this DI, this incremental distance, times the force that you applied at that measure to create that measurement. So if you take DI times the force, that will give you the work at that step, okay? So to get the total work done, we have to add up all 4 of these incremental steps for the work. So we have to add the work done in step 1 plus the work done in step 2 plus the work done in step 3 plus the work done in step 4 to get the total work done. I'm going to show you how you can do these calculations in a spreadsheet, which is what we are going to use when we are in lab. So we're going to have this spreadsheet that I'm going to show you in just a minute, and we're going to use that in lab. But before I do that, I want to show you a little bit more about what's happening here with our work is equal to the sum of the force times the distance. I want to show you what this problem looks like graphically as well, maybe a different way to think about it. So we saw that equation that said that the total work is equal to the sum of I equals 1 to n of the force applied at each measurement times the incremental distance we have to stretch the spring over each, for each measurement, okay? And this is also the same thing as the work done at each one of those incremental measurements or incremental steps, okay? And so then that's just equal to F1 D1 plus F2 D2 plus F3 D3, so on, okay? Or you could write it as work 1 plus work 2. This is the work done over each one of those incremental steps that we're stretching the spring, okay? So when we have a constant force that we apply over some distance, we do work, okay? And so if we have a graph here where distance is on our horizontal axis, force is on our vertical axis, if we apply a constant force over some distance, this is what the graph looks like, okay? And the work is our force times our distance, okay? The work done by this constant force is the force times the distance. Well, I've just drawn here a graph of a constant force being applied over some distance. And look at what we have here. We have an area that's the shape of a rectangle that has a height of S and a length of D. So we're essentially, when we're finding the work, we're finding the area, we call it the area underneath the curve of a force versus distance graph. Here we have the force on the vertical axis, D on the horizontal axis. If we're taking the area of a rectangle, that's the length times the width. In this case, the length is distance D, and the width is the force that's applied. And so whenever we are taking a work, we're also taking the area underneath the force versus distance graph. And this is what it looks like when it's a constant force, which is really easy and less interesting, I would say. Now what happens if we have a force that varies over time? Let's say that our force does something like this over distance. Okay, that's not an easy area that we can find. That's not, an easy area underneath the curve that we could calculate. It's sort of, it curves, it's not a linear line. Okay, so what you can do is you can break it up into little bitty segments and find the area that way. And so what we do in calculus, this is something called a Riemann sum, is that you could break up all of this area underneath the curve into these long, skinny rectangles. You calculate the area of each one of these long, skinny rectangles and you add them together, and that in the end is going to get you somewhat close to that total area underneath the curve, okay? And the skinnier and skinnier and skinnier you make these little rectangles here, the closer you're going to get to the actual value for the work done by a variable force over a distance. So this black little tall rectangle that I've colored in, that would be representative of one of these little incremental steps that we can make that has a width of, we call it DI, and a height of FI. So for whatever step you're on, you stretch the spring by some distance, small, tiny distance, DI, between the previous measurement, and you see what was the force you needed to have to stretch the spring over that little increment. And then what you have is a little tiny rectangle that would give you the work done over that little step. And the work done over that little step, W sub I, equals the height of this rectangle, which is the force over that little step, times the width of this little rectangle, which is the incremental distance that you pulled the spring over that step. And that gives you the work done for that little step. And so you find the sum of all the work that you do over each one of those incremental steps and add it together. That gives you the total work. And so that's what we're doing here. And yes, the smaller and smaller and smaller you make those incremental distances, the closer and closer and closer you're going to get to the actual value for the total work done. And then you could learn all the proper techniques to do a full-on integral, and you could also calculate it that way too. But this is how we calculate integrals in computer programming, by doing these little steps like this. So it has applications in real world. Okay, so you're going to have a spreadsheet that you can open, and you can do these calculations inside the spreadsheet. And I highly recommend doing it and practicing with it with these problems for the pre-lab, so that we can use it for the lab too. Trust me, you're going to want to use Excel to keep track of all of your columns, and Excel can even perform some calculations for you. So we are going to use some values for a problem that I have here right in front of me. This is exactly the method I'm going to show you right now, is exactly what you're going to do to solve questions 4 and 5 for the pre-lab, okay? So the problem that you have to solve for both questions 4 and 5, what is the total work in joules for the following set of data? You have 4 measurements, and I'm going to use some numbers here. For my first measurement, I stretch the spring a distance of 1.34 centimeters from equilibrium, and the force I have to apply was 19.1 newtons. Okay, you see how I've put the units of my measurement in the column here. So that tells me that every unit, or every number I'm putting in this column, has that same unit. For my second measurement, I had to stretch my spring 2.04 centimeters from equilibrium, and that required a force of 33.8 newtons. And then for my third measurement, I had to stretch the spring 4.42 centimeters from equilibrium, and that required a force of 52.2 newtons. And then for the final one, I stretched a total of 8.05 centimeters from equilibrium, and that required a lot of force, 153 newtons. Okay, so this quantity DI here, remember that's the incremental distance between the previous measurement and where you took this this measurement that we're working on here. Okay, so I didn't have a previous measurement for this first one here. For this first one here, I stretched my my spring 1.34 centimeters from equilibrium. So I'm just comparing it to 0. So my incremental distance here for the first one would just be the same as x sub I here, 1.34 centimeters. For my second measurement, the incremental distance that I stretched this spring from the previous measurement is going to equal here x sub I2 minus x sub I1. And see how I use the formula here in order to automatically do it for me. Okay, so 2.04 minus 1.35, that's the incremental distance, d2, that I had to stretch my spring compared to the previous measurement that I just took. And for the next one, my incremental distance is going to equal my current measurement from equilibrium minus the previous distance stretched from equilibrium. So 4.42 centimeters minus 2.04 centimeters gives me 2.38 centimeters. And then for the final measurement, my incremental distance I stretched from the previous measurement is going to equal 8.05 minus 4.42. Okay, so these are my incremental distances that I've stretched between the previous measurement, okay? And that's what I'm looking for DI. Then to calculate the work done for each step, the work done for each step is going to equal to the force that we had to apply on the spring gauge for each step times the incremental distance, okay? But remember that the work has to be in units of joules, okay? So that means to get units of joules, I have to take my force in newtons times my distance in meters. The way I've set up my chart here, or my spreadsheet, the incremental distance is in units of centimeters. So over here up in my formula for the cell, if I want to put DI, when I'm calculating the work, which is the force times the distance, I have to get that work in units of meters. So what I can do is I can take here where it says D4 to represent the quantity here that's shaded in red. I can take D4 and divide it by 100, and that will give me that distance in meters multiplied here, okay? And so then I can drag and pull down, copy and paste this equation essentially. And so then we can double check for each one of these measurements to find the work done for that step. I have to take the force at that step times the incremental distance for that step, but I have to divide that distance by 100 so that I can put it into units of meters, so that when I multiply my force times my distance, I have units of joules, okay? If you leave it here as just 1.34 centimeters and don't change it to units of meters when you're multiplying the distance and the force, then you're not going to be in the right units, okay? Then my total work is going to be the sum of the work from each individual step. So I can say here equals, the total work equals, so I can say the total work equals the sum of all of my work for the individual steps, okay? And I hit enter there. So we want the formula to say equals, and then you can use this Excel function sum, and then my work here is in cell E4 to E7, so that's what this means here. I'm going to sum everything up from cell E4 to E7, and I'm going to put it right here where I stuck it. If you aren't comfortable using the Excel functions, you can say that the total work equals that cell plus this cell plus this cell plus this cell, okay? And you'll still get the same answer. So then my total work in joules will be the sum of the work from the first step plus the second plus the third plus the fourth, and that will equal our 7.29 joules for the total work. Problem 5 is exactly the same, so maybe you just copy and paste this, these little charts here, and you can reuse that in order to do the calculation. I think it's a little bit easier and simpler to do it here in Excel for this one problem, but you could also do it by hand if you wanted to.